Hello, am I audible? Hello. Okay. So just give me some time. Okay, fine. So is there any question from the previous class? You can ask me any question from the previous class, and then we'll start density of states. And I think the due date for assignment 8 is over, and also I have seen that the solution is also updated. So is there any problem understanding any of the problems, or you have understood all the problems there? Everyone solved assignment 8? If there is any problem, we will discuss maybe later, but let me first introduce density, density of states, and then we will calculate density of states for free electron in 1D, 2D and 3D system. So there are a lot of questions from density of states, specifically in the competitive exams. The questions are asked from the density of states. So we will solve for today's class, we will dedicatedly solve few problems from the density of states calculation. So let me share my screen first. Sorry. Screen share. Control. I hope my screen is visible. So please, class number 9. Today is 23rd September. So today we are gonna discuss about density of states. So density of states means the number of energy state per unit energy. So it is defined by D of E. In general, it is defined by D of E, or you can see somewhere it is defined of G of P. So it's a function of energy. So I'll write. So density of states gives the number of allowed states per volume at a given energy. So it will be definitely a function of energy because it gives the number of allowed states per volume at a given energy. So we are going to calculate density of state for parabolic dispersion relation in 1D, 2D and 3D. So what do you mean by parabolic relation? So you know that for the free electron the energy dispersion is given by h bar square k square by twice m. So if the electron energy is given by this equation 1, then what will be the density of states for 1D system, 2D system and 3D system? So all the dispersion relation I have already written for this free electron. Now first we will start with 3D. So for 3D, so let me first calculate for 3D. I will calculate for 3D, then you can calculate for 2D and 1D as well. So we'll solve all of this in the class. So there is one allowed, you know, from quantum mechanics you can show that there is one allowed value of k per volume 2 pi by L cube. Yeah. So one states is there per volume 2 pi by L cube in K space. So that comes from the boundary condition in K. So in Kx, Ky, Kz can have value of L by 2 pi. So let's say if these are the Kx value, then the difference in between 2 points is L by 2 pi. So minimum volume for one energy states is 2 pi cube by L, or L cube by 2 pi cube. So let me, which is equal to L cube is V by 2 pi cube. Allowed values of K per unit volume. Of the K space. So there is one allowed value of K per this volume 2 pi by L cube volume, and then what will be the number of K states available in so what will be the number of allowed values of K per unit volume, and that will be the opposite of this. So reciprocal of this, that is L cube by 2 pi, that is V by 2 pi cube. And the volume of the specimen which we are considering, let's say the volume of the specimen is V. Which is L cube. Now we need to calculate what is the total number of modes with wave vector less than K. So we will calculate the number of modes. The number of modes with wave vector less than K is V by 2 pi cube times, this is the volume, times this is the number of states times the volume of a sphere of radius of a sphere of radius k. So first we have said that in per unit volume we have this number of states, v by 2 pi cube number of states. Now it's in 3D, it's like a sphere with radius k. So we need to calculate how many states are there in this volume with radius k. So per unit volume we know the number of states is v by 2 pi cube. So in this volume what will be the so the volume of this is 4 by 3 pi k cube. So we need to multiply 4 by 3 pi cube with the number of states per unit volume, and that will be thus the number of total number of modes, that is n, is equal to g bar. So g bar is for the spin degeneracy. So you can have two electrons, electron spin is half, so g is 2. For electron g you can take just 2. So g bar divided by v by 2 pi cube into 4 by 3 pi k cube. So this is the total number of modes per unit volume, this one, and this is the volume. So we can find out what is the number of volume. So g bar is the degeneracy factor, and for electron you know that g bar is 2. G bar is 2 for electron, or spin of fermions it is 2. So the density of states in 3D will be d of 3D. So this so 3D is because of we are calculating at for the 3D system. So it will be g bar into 1 upon v into del n del e. Sorry, g bar is not 1 by v into del n e del e. So what we have said before, that the density of state is the number of allowed states per unit volume per unit energy for a particular energy. So density of states is defined by this 1 by v into del n del e. For any system we will calculate by this formula 1 by v into del n del e, and if we calculate del n del e, so you need to calculate del n del e. So you can do chain rule here, 1 by v into del n del k into del k del e. Or you can show that this will be equal to g bar by 2 pi square into k square into dk de, because we can calculate del n del k from this expression. What is del n del k? G bar into v by 2 pi cube into 4 by 3 into pi into 3 k square. So this 3 cancels out, 4 pi. So g bar into v divided by this is 8 pi cube. So basically we will have 2 pi square into k square, right? Yeah. So del n by del e is this value. So we have replaced this del n del e here, and we will get that it is g bar by 2 pi square k square dk de. Now for this dispersion relation, equation 1, you can calculate dk de. So E is given as h bar square k square by twice m. What is de dk? De dk is h bar square k by m. So you will put this value in the expression of d3d, which is g bar by 2 pi square into k square into dk de, which is opposite of this, that is m by h bar square k. So we will ultimately get g bar by twice, it is not, oh sorry, it is 2 pi square, not whole square, it's 2 pi square. So g bar by 2 pi square into mk by h bar square. So this is the density of states in terms of k, but we need to write it in terms of energy. So from this you can find out that k equal to root over of 2me by h bar. So if you put this value here, you will get g bar m into root over of 2me, and there is one h bar there, so it will be h bar cube. Or you can write in this way also, g bar by 2 pi square into m by h bar square to the power 3 by 2 into root over of 2e. So you can see that for 3D system and with parabolic dispersion, the density of states d3de is proportional to root over of e to the power half is root over of e, and this all of these are constants because m, h bar square, g bar, everything is constant. So for 3D system we see that the density of states is proportional to e to the power half. Now in the same way you can calculate the density of states for 2D system as well. So if you have any doubt for 3D system, you can ask, and if you clear this calculation, then you can definitely calculate it for 2D as well. Just for 2D, the allowed state, the allowed value of k per area will be 2 pi by L square. In terms of cube, there will be square, and in the place of volume you need to take an area of a circular area. So if you understood this calculation, then you can calculate the density of states for 2D system as well. Is there any question for this calculation? What we did is we first calculated what is the number of k states per unit volume, then we multiplied that number of states with the volume of the sphere. So that will be the number of allowed states n, and so what we need to do is find the number of states per unit volume and with respect to for a particular energy. So we need to do we need to find out 1 by v del n del e, that is this value. So you know n, you can derive it with respect to e, and you can find out. So you can do one more thing here in so in the place of k you can write in terms of e. So in terms of e you can write there, and you can derivative, you don't need to do the chain rule, and you can straightforwardly calculate this one. Is there any doubt? So if this is clear, please can you calculate for 2D system? The dispersion relation is same, so this is the dispersion relation, it will be same, and you need to calculate this for a 2D system. Can you do that? That was density of states for 3D. We will do density of states in 2D. The dispersion is again same, E equal to h bar square k square by 2i same. So you first need to calculate what is the n. The same way I did for 3D, calculate what is n, and then calculate del n del e maybe. So you write n in terms of energy, you can replace it anytime, then calculate del n del e, and then density of state dE is just 1 by v del n del e. So please do that for 2D system. Hello. Did anyone calculate the density of states in 2D for this parabolic dispersion? And can you tell me what is the dependence with energy? You need to do it actually. So it is the replicate of this, just you. So I'll just copy this because it's almost same. So there is one allowed value of K per volume 2 pi by L square. Sorry. And in K space, or L cube L square by 2 pi square, L square by 2 pi square, which is area A by 2 pi square allowed values of K per unit volume. Sorry, per unit area. There will be per unit area. So this number of allowed values of K per unit area. So in 2D, the number of modes that a circle of radius K encloses is, so the number of so in 2D you will have a circular this kind of region. So if this is K, so this will be the number of modes in this area. So the area will be pi K square. So the number of modes that a circle of radius K encloses is n equal to g bar into L by 2 pi whole square, or it is A by 2 pi whole square. This is the allowed value per unit area into the area. The area is pi K square. So it is actually g bar A by 4 pi into K square. Now you can write this n in terms of energy. What is K square? So g bar A by 4 pi into K square. K square is from this relation. From this relation you can see that K square equal to 2me by h bar square. So replace that value 2me by h bar square. So you will get g bar A by 2 pi h bar square into me. So then the density of states in 2D is d of 2D is equal to 1 by A into del n del E. So what will be this value? 1 by A into, so I am going to derivative with respect to E for this one. So this is g bar A by 2 pi h bar square. These are constant, m is also constant, and del E is 1. So you can see that there is no energy dependence for 2D. So it is just g bar m by 2 pi h bar square. So in 2D the density of states is constant. It does not depend on energy. It is a function of energy, but in 2D for parabolic dispersion the density of states is constant and it does not depend on energy, that is proportional to e to the power 0. Is it clear up to this? how the density of states is constant for 2D system. If it is clear, then let's calculate this for density of states for 1D system. Density of states in 1D. So for 1D system, the number of modes enclosed by the range. So in 1D, we'll consider length from minus k to plus k. Let's say in between it is 0, from minus k to plus k. So I'm directly going to write, so the number of allowed states, the number of modes enclosed by the range minus k to plus k is given by n equal to g bar into L by 2 pi. So L by 2 pi is the number of modes at in length L into 2k. Into 2k, this is the length of this. So at unit length, these are the number of modes, and we need to multiply it with the total length. So again you can write this in terms of energy. So it will be L by pi into k. So h bar square k square by twice m equal to E. What will be k then? K equal to 2me root over of 2me by h bar. So just put it down here, 2me by h bar. Now the density of states in 1D is thus so what will be the density of states in 1D? It will be one by L into del N del E. So you see the difference in for 3D it was 1 by V del N del E, for 2D it is 1 by A del N del E, and for 1D it is 1 by L del N del E, and it is 1 by L. So 1 by L is there into this is N, so you can calculate del N del E from this expression, that is G bar L by pi into root over 2m by h bar. And what is e to the power half derivative with respect to dE? Will be half 1 by 2 root t. So ultimately LL gets cancels out, so there will be root 2 in the between. So G bar by pi into root over of m by 2 h bar square E. Yes, so you can see that in 1D for parabolic dispersion, the density of states is proportional to e to the power minus of, or 1 by e to the root e. So you can remember these expressions for this parabolic dispersion, that for 3D it was proportional to e, For 2D it is e to the power 0, and for 3D it is 1 by root e. So this is for this parabolic dispersion, E equal to h bar square k square by 2m. Now in the similar way, can you calculate the energy dispersion for a massless Dirac system? So now if I change the energy dispersion, this energy dispersion if I change, and if I give you an energy dispersion like, so let me write it down for massless Dirac. Density of states for massless Dirac system. So in terms of K, it is h bar Vf K. This is the energy dispersion for massless Dirac system. So h bar and Vf are constant. These are, you can take as constant and does not depend on energy. And consider this. So using this dispersion relation, if you let's say this is equation number 2. Can you shortly calculate what is the expression for density of states in 1D, 2D and 3D? So everything will be same. Hello, am I audible? I think I lost the connection in between. Hello, hello, hello.
Yes, sir, audible, sir.
Okay, okay. Yeah, so what I was saying ki, for the previous case, we considered this energy dispersion E equal to h bar square k square by 2m, and followed this process. So following the same process, can you calculate for massless Dirac system where energy dispersion is just changed? So in place of this energy dispersion, we are having this energy dispersion. So can you calculate the density of states for 1D, 2D and 3D and see how is the energy is depending on the density of, so the density of states depends on the energy. Can you show for 2D, 3D and 1D case? So everything will be same, just when you are replacing k, so we are replacing k as root over 2me by h bar. Now you need to replace k as e by h bar Vf. So please calculate this density of states and let me know what is the answer. Am I audible? Are you
Yes, sir.
calculating? Yeah, are you calculating the density of states? So
Sir.
yeah, so okay. Whatever you calculate, please update.
Hello, sir.
Yes, did you calculate it
Sir, I have calculated density of states in one dimension.
for one dimension? And what is the answer?
Sir, is it is independent of energy.
Yes, for 1D it is independent of energy. Like for the parabolic dispersion it was in 2D, but for this dispersion it is for 1D. Yes, you are correct. Can you calculate for 2D and 3D also?
No, sir, I am calculating, sir.
Yeah, sure. So I am writing the answer. You can check. So for 1D this will be g bar by pi into 1 by h bar vf. Sorry. So you can see that this is actually independent of energy. So it is proportional to e to the power 0. So this is actually constant.
Hello, sir.
Yes, have you calculated for 2D?
Yes, sir. Sir, density of states is directly proportional to the energy.
Correct. Density of states in 2D is proportional to the energy. So in 2D the energy is g bar by 2 pi e by h bar square vf square. So you can see that it is proportional to the energy. So you can definitely also calculate for 3D. What about others? You guys are calculating or you can't calculate it? Do I need to solve for 1D and 2D? Or did you get the answer? For 1D it is constant and for 2D it is proportional to energy. see, everything will be same, like in this problem. So in 1D it was 2k, right? So in 2k, so in place of k you will write h bar e by h bar vf, so it will be proportional to e. But when you derivative with respect to e, that you will go and you will see that the density of states will be constant and it is independent of e. So I don't think I'm gonna solve for that value.
Hello, sir.
Yeah, for 3D, what is the answer?
Sir, density of states in 3D is directly proportional to the square of the energy.
Exactly. So for 3D, the answer is g bar by 2 pi square e square by h bar cube vf cube. So you can see that the energies, so the density of states is proportional to energy square. Is there any doubt? Could you calculate this, or do I need to calculate it? Then we can solve few problems from this density of states.
Hello, sir.
Yes. Hello.
Sir, why you introduced G bar in density of states?
So G bar is actually the degeneracy factor for electron. You know that for its spin half, the two electron can have same energy, right? So in a same state,
Yeah.
two electron can stay in the same state. We, matlab, you know the Pauli exclusion principle, right? So according to Pauli exclusion principle, in one state, two electron can with spin half and one with spin down. So two electron can stay in the same state. So we are calculating density of states. So that's why we have introduced this G bar, which is equal to 2 for electrons. That is for any spin half fermions, this G bar is 2. So this is actually 2s plus 1 s. This G bar is actually 2s plus 1, where s is the spin. So 2 into half plus 1, that is actually 2. So this is just the degeneracy factor. If you consider spinless system, then this G bar is not there, then it is just 1. But for spin up system it is 2. Do you understand?
Yes, sir.
So yeah, so then let's solve few problems. So yeah, so we can start solving few problems. For a two-dimensional free electron gas, the electron density is n, and the Fermi energy and the Fermi energy EF are related by A is n equal to 2 MEF by to the power 3 by 2 divided by 3 pi square h bar cube. Then option B is n equal to MEF divided by pi h bar square. Option C is n equal to MEF by 2 pi h bar square, and option D is n equal to 2 to the power 1/3 MEF to the power 1/3 divided by pi h bar. So need to calculate this one. So you need to use the density of states for 2D also, because you know that the number of states in is 0 to EF, GE, DE, GE, DE, FE. GE, FE, DE. So GE is the density of states and FE is the Fermi-Dirac distribution function which is, so at 0 temperature FE equal to 0 for E greater than EF, and FE equal to 1 for E less than EF. So this is actually 0 to infinity, but then this will be cut off because of this function, because if you take greater than EF, then epsilon FE is just 0. So yeah, it is actually 0 to infinity. So using this relation, you also know the GE for this two-dimensional free electron gas. So this free electron gas, it says in the question, so you can use E equal to h bar square k square by 2m relation, and for that case you know what is the density of state GE for 2D system, and then calculate what is the value. So I think so you also need to take into account the spin of electron, because it is talking about electron. So you need to take into account the G factor, which is 2. So can you calculate this with this formula?
Sir, what are the options?
Okay, so these are the options.
Sir, option second.
Option B, yes, option B is correct. So you already know that density of state. G of E. So we have calculated it for 2D system. And what was the value? Yeah, this is. So 2m by 2 pi h bar square. 2m by g bar is 2, so 2m by 2 pi h bar square. Which will be that is equal to m by pi h bar square. So we have already taken it for per unit, so this is actually small, this will be small, and because we have already taken into account 1 by L square, we divided already, so it is actually n. So n is equal to 0 to epsilon f or ef. So you can divide it into region. One is ef GED FE DE plus EF to infinity GE FE DE. So for this region, this is 0, because for 0 temperature we see that Fe equal to 0 for E greater than EF. So you are only left with this part. Now GE is m by pi h bar square into DE, and the other parts are constant. And you have integration of D, which will give us EF. So you can see that n will be m EF pi h bar square. That is option B is correct. The correct answer is option B. Is it clear, or is there any question? If is there any question, you can ask me. I'll try to answer. So let me know. So it was for 2D. So can you calculate it for 3D also? So what would be the relation of n with EF for 3D? Can you calculate? So this is for 2D. I want the same kind of relation with n and EF in 3D. So it's same way you need to do, and only the change is the density of states will change, and other things are same. So please do it for 3D, and then we'll solve a few problems which we use this relation of n and EF for 3D. Calculate for 3D and please say the answer. So for 3D, you know that that form is already known. So G is given. Where is this formula? Yeah. So this is the formula for 3D. So I'm gonna just copy this. And G bar will be 2 because we are considering electron. And you need to replace this in the expression of n. So n will be 0 to EF 2 by 2 pi, so pi 1 by pi square into m by h bar square to the power 3 by 2 into root 2e into dE. So I am taking this from this line, I am considering from this line. So this part is 0 and this part is Fe is 1 for this. So from this line what we will get, other things are constant. So 1 by root 2 by pi square, let's say root 2 by pi square into m by h bar square to the power 3 by 2. Now what is root e dE? So it will be e to the power 3 by 2 divided by 3 by 2, 0 to EF, which is so 3 by 2 is 2 by 3. So 2 root 2 by 3 pi square into m h bar square to the power 3 by 2 into EF to the power 3 by 2. So this will be the answer. And if you write EF in terms of n, so this is n in terms of EF, and you can also do the opposite. So it will be 3 pi square n by 2 root 2 into h bar square by m to the power 3 by 2 equal to EF to the power 3 by 2. Can we put this inside? So 2 to the power 3 by 2 is actually 2 into root 2. Yeah, so we can put this inside. So 2 m by h bar square. So 2 root 2 can be put inside, which implies that EF equal to h bar square by 2m into 3 pi square n to the power 2 by 3. So what I did is I multiplied, so I powered it by 2 by 3 in both sides. So you will get EF equal to h bar square by 2m 3 pi square n into 2f3. So this relation we will use to calculate the next question, to solve the next question. Yeah. So in this question, the question is by the way, if you have any doubt for the 3D case, how did I calculate this EF with an n, the relation of EF with n, if you have doubt you can ask me. So if there is no doubt, we will calculate this question. If the number density the number density of a free electron gas in 3 dimensions is increased 8 times its Fermi temperature will increase by a factor of 4. B is decreased by a factor of 4. C is increased by a factor of 8. And D is decrease by a factor of 8. So if the number density of a free electron gas in 3 dimension is increased 8 times, its Fermi temperature will increase or decrease. So first you can calculate what will be the EF. If we increase the density by 8 times, then how the Fermi energy will change, and then you can definitely calculate what is the dependence of Fermi energy also, because you know that the Fermi energy EF is actually kB into TF. So however this will change, TF will change in the same way. So calculate EF for these two and let me know the answer. Option A. So let me check. So yeah, option A is correct. So you know this formula that EF is equal to h bar square by 2m into 3 pi square n to the power 2 by 3, right? Yes, so this is the formula. Now you see that EF is actually proportional to n to the power 2 by 3. So for the first case, if you take it is EF1, then it is n to the power 2 by 3. Now for when we have increased n, then it will be EF2, and that will be how many times we have increased? 8 times. So 8n into 2 by 3. 8n into 2 by 3. And if we do EF1 by EF2, so it is proportional to actually. The rest is constant. So EF2 by EF1 is 8 to the power 8 n to the power 2 by 3 divided by n to the power 2 by 3. So it is just 8 to the power 2 by 3, and 8 is actually 2 cube, so it is 4. Since EF is equal to KB into TF, you can also write that TF2 by TF1, this is also equal to 4. So it will increase by a factor of 4. So since from this relation you can argue that the temperature, the Fermi temperature will increase, Fermi temperature will increase by a factor of 4. So option A is correct. Is there any doubt? First we have calculated the relation between EF and N in 3D, and then we have calculated EF for two different densities and took the ratio and find out that it is equal to 4. So it will increase by a factor of 4. Is there any doubt, or if everybody understood? See, if you have any question you can ask. You are not actually asking any question.
Sir, how can calculate the extrinsic semiconductor P type and N type?
You want to calculate what? The number of density.
Not for extrinsic carrier configuration.
I don't get it. Like, is this question in any assignment? Can you send me the question you are talking about, or maybe? So what is for extrinsic semiconductor? What do you want to calculate?
I think
So let's say extrinsic semiconductor we are talking, and we want to calculate n. So I have seen few problems. I think I don't think in this year assignments there was any question from this semiconductor. Can you particularly send me the question? Maybe then we can discuss about it. I can provide my email ID. If you want to send any question, you can send. So in the chat box, let me write down the email. Sorry. Oh god, I cannot write the email. Okay, so actually my keyboard that at the rate is not working. Is there any manual keyboard here? Wait a minute, just I'll write down my email using the manual keyboard. On screen keyboard. Yeah, so Sanjay is at the ship the IITK dot fu dot in. So this is my email ID. If you are talking about any particular question, you can send this to my email ID, and we will discuss this in the next class, or I can also send the solution in through email. So today I was going to solve problems from density of states only. There are a few more questions which I want to solve. So let me check. Yeah, so I think we have already solved it, but still, since this question is there, so question 3. Sorry, that was second question. The third question is if the energy dispersion of a two-dimensional two-dimensional electron system is E equal to UH bar K, where U is the velocity and K is the momentum, then the density of states which is dE depends on the energy as option A is 1 by root E, option B root over of E, option C is E, and option D is constant. So I think I have already shown you what is the answer, but still can you tell me immediately what is the answer? So this question I have already solved, but since this is particularly so yeah, I did not solve particularly, but I have written the answer there. Anybody? See, this problem, so when I was discussing the theory of density of states, I've already discussed it. So this is same to this this expression, right? In just in place of Vf we have u. So for 2D we'll solve in the same way. What do we get? This is the so this is the g n. So n we can write from this expression. This will not change, right? So copy. If I copy this for 2D, so total number of modes n equal to this. Now the energy dispersion is given as E equal to U h bar k. So from there you can calculate k in terms of E, which is E by U h bar. Now replace this in the expression of n as g bar a by 4 pi into k square, and k square is E square by U square h bar square. Then what is the density of states dE? Density of states is 1 by A into dN dE. So A 1 by A is there, g bar A by 4 pi into 1 by U square h bar square, and derivative of E square is 2E. Then A cancels out, this 2 will get this A, so g bar by 2 pi into E by U square h bar square. So it is proportional to E. So option C should be correct. It is proportional to E. I have also written down the expression for different case. So this is the correct. This is the expression we are talking about. So for 2D, this will be the expression, and it is proportional to E. So we have also calculated it, and I have shown this option C is correct. Option C. Is there any doubt? Now there is this question. Let me calculate this. So if you have understood this, you can calculate this also. Okay. Now we'll. So this was question number 4. Consider electrons in graphene. Electrons in graphene, which is planar monoatomic layer of carbon atoms. If the dispersion relation if the dispersion relation of the electrons okay, let me add, some people are waiting. So if the dispersion relation of the electrons is taken to be epsilon k is equal to ck, where c is a constant, over the entire k space, then the Fermi energy epsilon f depends on the number density of electrons rho s. So there are a few options. Let me write down the option. Who wants to join? Okay, Prithviraj. Epsilon a proportional to rho to the power half. Option B is epsilon a proportional to rho. Sorry, option C is epsilon a proportional to rho to the power 2 by 3, and option D is epsilon a is proportional to rho to the power 1 by 3. So these are the options. Calculate this. So this kind of problem I have already solved. This was which question? So question 2, no, question 1. So question 1 was also similar to this one. So please look onto question 1 and please solve this one. So at least did you try to calculate? So we are considering electrons in graphene. So graphene is a planar system, that is a 2D system, which is a planar monoatomic layer of carbon atoms. If the dispersion relation of the electrons is taken to be epsilon k equal to ck, where c is constant over the entire k space, then the Fermi energy epsilon f depends on the number density of electrons rho s. So what we are given that epsilon f is equal to ck. So we have already calculated. So this is the thing for this kind of dispersion. We know what is the density of states. So the density of states GE. So we will write density of states at G or D. Everything is fine. So their C is actually UH bar. So in the place of UH bar we are having C. So replace the UH bar as C and you will get the density of states. So density of states dE is 2 by 2 pi. So G bar is 2 actually. So 2 by 2 pi into E by C square. That is 1 by pi C square into E, or E by pi C square. So this is the density of states. Now you have to calculate the Fermi energy depends on number density. So you know that number density n is 0 to EF GE DE at 0 temperature, because we have already calculated this problem. So GE is E by pi C square into, okay, so it is actually expressed as rho, not n. So rho we can calculate, so we can write it just rho. So it will be pi E by pi C square into, so 0 to epsilon f or EF into DE. So this is the constant part which will come out, and ED is E square by 2, so it is just EF square by 2. So the dependence of energy, so EF square is 2 pi C square rho, which implies that EF is actually 2 pi C square root over of 2 pi C square. That means it is proportional to root or rho to the power half. That means option A is correct, because in option A you can see that epsilon f is proportional to rho to the power half. Sorry. So option A is correct. The correct answer is Is this clear? So everything we are calculating at 0 temperature, because otherwise we cannot divide this 0 to epsilon f and epsilon f to infinity, because we are taking this consideration that if e equal to 1 for epsilon f less than epsilon and equal to 0 for epsilon f greater than epsilon. So this is valid only for t equal to 0 Kelvin. So we are calculating these problems for t equal to 0 Kelvin. If you have doubt, you can ask, or we'll solve a new problem. So if you don't solve it by yourself, it will not help actually, because these questions are pretty easy and straightforward question. So let me solve this next question. An ideal gas of non-relativistic fermions in 3 dimension is at 0 Kelvin when both the number density and mass of the particles are doubled, then the energy per particle is multiplied by a factor option A is 2 to the power half, option B is 1, option C is 2 to the power 1 by 3, and option D is 2 to the power minus 1 by 3. Yes. So similar way you can calculate this also. Please do that. Hello, are you calculating this? We don't have much time. We have solved more problems also. Sorry. So okay. So an ideal gas of relativistic fermions in 3 dimension is at 0 Kelvin when both the number density and mass of the particles are doubled. So for 3D and 3D particle, for a particle in 3D, we know that the EF is related to this. Okay, so this I will copy. Let me write down this here. Sorry. Oh no, it was not copied, I guess. So yeah, in 3D this is the relation of Fermi energy with density. So it says that if the mass, when both the number density and mass of the particles are double, then the energy per particle is multiplied by which factor? Energy per particle. Okay, so yeah, so this is not actually what we were looking for. We had to calculate the density of states first. Let me show you. So this is question number 20. Let me check the question again. So when we double the energy, double the density and as well as the mass, then what will be the new Fermi energy? The new Fermi energy will be h bar square by 4m into 3 pi square into 2n to the power 2 by 3. That will be equal to h bar square by 2m into 3 pi square n to the power 2 by 3, and we can keep this out, that is 2 to the power 2 by 3 by 2 is out, and this can be written as EF. So this part is actually EF, so this is EF into 2 to the power minus 1 by 3. So then the energy per particle is multiplied by 2 to the power minus 1 by 3. So option D should be correct. Yes, then the right answer is option D. So let me, okay, so we have calculated 5 questions, solved 5 questions, and let me check if there is, so 13, 18, so 39 and 40 is also from this 39 and 40. Yeah, so this is a numerical kind of problem, you need to calculate it. Let me write down the question first. So consider a two-dimensional electron gas with a density of 10 to the power 19 meters square. The Fermi energy of the system is in electron volt unit. You need to calculate, where ME is given mass of electron is 9.31 into 10 to the power minus 31 kg, and H is also given 6.626 into 10 to the power minus 34 joule second, and E is, you already know, 1.602 into 10 to the power minus 19 coulomb. So these are the value, these are the thing are given up to 2 decimal places. You need to calculate in unit of electron volt. 2.34 electron volt. Option C is 1.22 electron volt, and option D is 5.25 electron volt. So please calculate this. So consider a two-dimensional electron gas with a density of 10 to the power 19 meter square inverse. The Fermi energy of the system you need to calculate. So since nothing is told in the question, we will consider this as a free electron gas. So for free electron gas in 2D, I think we have shown the relation of this h bar square EF and N. So you use this relation and calculate. So did you calculate it? 2.38 electron volt you are getting. So let me see. 2.34 is option B. Okay. So yeah, option B is correct. So what relation we'll use is, we have already calculated it and we'll just use the relation there. So this relation we'll use N equal to m EF by pi h bar square. So for 2D we know that N equal to, for 2D system, N equal to m EF by pi h bar. Is it correct? m EF by pi h bar square. Okay. What will be the relation of EF and N? Then EF equal to pi h bar square by m into N. So the Fermi energy of the system, the N is given is 10 to the power 19. Sorry, N is 10 to the power 19 meter square. H bar and M are also given in the question. H bar is 6.626. So if you convert it, so it will be 1.05 into 10 to the power minus 34 joule second. Then N is given, M is also given, which is 9.1 into 10 to the power minus 31 kg. Now put this in AF and you will get pi into 1.05 into 10 to the power minus 34 square into N, which is 10 to the power 19, divided by M, 9.1 into 10 to the power minus 31. This is in joule. So what will be the value? Let me calculate it in the calculator. So my microphone was off, I guess. So you guys could have told me that my microphone was off. Hello, am I audible now? Hello.
Yes, sir. Yes, sir.
Yeah, so it was off before. So we have used that relation of for 2D system. We have already calculated what is the relation between EF and N. So we have used that relation and put all the values. So can anyone tell me what is the? So let me check if I can calculate in the calculator.
So 2.38 electron volts.
Okay, so you are getting 2.343 electron volt. Everyone else agree with this? So let me still calculate it. This divided by 9.1. So what I was getting is 0.38 into 10 to the power minus something in joule. So minus what? 34 into 2 minus 19 plus minus 18. So in you need to convert it to electron volt, and you have to divide it by 1.6 into 10 to the power minus 19 joules. So it is in electron volt. So 0.38 divided by 1.6, 2.38, yes. So it is 2.38 electron volt. So option B is correct. Option B, yes. So now given this theories, now you can calculate any problems from this density of states and number of electrons per unit volume. If you have any doubt, you can ask. Anyway, how what are the other TS solving? Can you tell me what are the other TS doing currently? Are they like teaching theory or solving problems? Is there anyone who is attending other classes? No one. Yeah, Vaishu, what are they teaching? Like they are solving problem or teaching theories? Yes, solid state physics definitely, but it's more of a solving problems or theory plus problems or just theory. Or is there any if you have any feedback from for this class, you can also we can also discuss, like, okay, theories and problems. So if you have any suggestion, you can give. So I think we have 3 more classes left. This is the 9th class. So if you have any suggestion or anything, you can give me. We can incorporate this in the next classes. Well, okay, so till now whatever we have learned, if you have any doubt, you can ask for today's class, let's say.
Sir, please upload today PDF in the link.
Okay, sure, I'll upload this. Did you get all the other PDFs which I have uploaded till now?
Okay, sir, got.
Okay, okay. So I don't think I can solve any more problem now. Already it's 7, and I have 2-3 more problems from density of states. Maybe we can continue in the next class and start some new topic and solve some new problems.
Okay, sir.
Yeah. So most probably we'll start with thermal conductivity and all.
Hello, sir.
Hello. Yes.
Sir, can you explain the effective mass?
Yeah. So you are not in the last class. Were you in the
Uh,
last class?
Sir, I have not attended.
Okay. So effective mass is like, so mathematically explaining, it is m star, which is given by h bar square by del 2 e del k2. So it is coming from this Schrodinger equation. You have to solve this and you will get the formula for this. And so this is basically the curvature of the band structure. So energy dispersion you will get, so E in terms of k, sorry. So basically it is not a scalar value, it is basically a tensor. So this is for isotropic case, but if it is not isotropic, then it is del 2 e del ki del kj. So you will be given energy dispersion in terms of, let's say, kx, ky and kz. Then you will get a matrix. For 3-dimensional case you will get 3 cross 3 matrix. Well, this will be mxx star, this is mxy star, this is mxz star, then this is myx star, and so on. This will be mzz star. So there will be 9 elements of this matrix. So this is the let me write it as m star. So this matrix is the effective mass tensor matrix. So in problems you will be given a dispersion relation of this kind, where it will depend on kx, ky and kz. Then you have to calculate each of these elements using this formula. So let's say I want to calculate mxy star. What you need to do is h bar square del 2 e del kx del ky. So first energy is given, then you can calculate del e del ky, then calculate del kx of this and put this in this value, and you can calculate m star xy, which is h bar square by this value. So I have uploaded the PDF in the Google Drive link. You can refer to this that PDF, and you can see that I have solved very few problems. So if you see that those problems, you can definitely understand that.
Okay, sir.
Yeah. Okay. So thank you. Then I'll end the class now. So thank you. Bye everyone.